All right, maybe I can go ahead and start. Hello, everyone. Good morning. So maybe I can just do like a look back and see what we did so far. So far, I think what we did was like describing motion, right, in 1 and 2 dimensions, and introducing vectors to do that more systematically. And then we started talking about Newton's laws. Newton had 3 laws. F was equal to ma, and there was like action reaction law, and if there was no force, there was no motion. And last week we talked about one of the most fundamental forces in nature, gravitational force, and we used that to describe things like planetary motion, for example, or like Kepler laws. So this week I think we are going to change gears a little bit, and we are going to introduce something new, work and energy. And you probably know from high school there are some problems that are actually very difficult to solve with like Newton's laws, but it's very easy once you look from the perspective of work and energy. So this is the reading assignment, and hopefully we'll solve these examples maybe today or tomorrow. So first, let's start with work done by a constant force. So here's the setup. Suppose you have some object that you want to move, and you are acting on it with some constant force. Let's assume this F is constant, and at the end of this whole action, you move this whole object from point here to here, which is some net displacement d vector. Okay. So the way to, so maybe I think it's best to define what it is first, and then maybe talk about it. So I want to define a work, which I show with W is equal to the parallel component of this force. Let me show this with F parallel times the parallel to the displacement and the total displacement D. Okay. So in this form, this is like a scalar quantity. So this F parallel is, of course, F, and you just project it to here. That's if you define this angle to be theta, F parallel is going to be F cosine theta. And if you substitute, of course, this is theta, but this theta is the angle between vectors F and vector displacement D. So, and of course, there's like a unit of this thing because force is in Newton. Okay, unit. Force is in Newton, and displacement is in meters, and this is generally called joule. It's identical with joule type. So I think there's like, we can already see some stuff about this. It's because of this angle dependence. For example, if force is perpendicular to the displacement, this theta is pi over 2, or like 90 degrees, and cosine of 90 degrees is 0. And force is perpendicular to displacement, that force is not doing any work, even if the object is moving. And here's the example. Suppose you are moving your groceries, and also we are supposing that you are moving with constant velocity. Even though you are applying a constant force to lift this package, right? Because there's like a gravity pulling it down, and you have to lift it so that it doesn't fall. So you're acting with some force, and you're coming back home or your dorm, you're moving with constant velocity. You may think that you are doing like a lot of work and you are tired, but feel from the physics point of view, we are not doing any work because this force F sub P is perpendicular to the displacement D. So you have to displace the object to be able to make a network. Okay, maybe I can write that. Force should result in displacement. Maybe for work. Because if you don't have displacement, you don't have work. Is that clear? Any questions? Simple stuff, right? I just define one thing, and that's work is equal to F times D. And F is a parallel component, so we had to take into account cosine. So let's just do an example and see how this thing works. Here's the example from your book. So example 2, determine the work a hiker must do on a 15.0 kilogram backpack to carry it up a hill of height h is equal to 10.0 meters, as shown in figure here. The hiker is going from here to here, and we are only the center of mass moves. Yes, exactly. Center. I think there must be net displacement of center of mass. Exactly. Right. So how do we do this problem?
You may ask something.
Yes.
I mean, if some, I mean, angular work was done on an object, center of mass doesn't change, but it gains a velocity or something like that.
Yes. Yes.
Does it also work?
Yes, it works. We'll come to that, right? We started simple, and then we'll come to this rotational work, and we'll also study that. You are right.
Okay.
But we don't want to complicate things from day one, right? We just want to first look at the linear motion, and then this rotational motion in a couple of weeks. So okay, so maybe I can just look at the maybe I can draw the free body diagram. There's like this hiker, and we are interested in the backpack. So there's some gravitational force. Let's call this G, and the hiker is lifting it up. There is some, let's call it, I don't know what I should call it, FP, force applied by the person. And using that definition we use here, work, okay, maybe I can lift this a little bit up. Okay. So W is equal to like F parallel times total displacement, and the displacement is along this direction, force is along this direction. I need to project this force along this direction. So I need this angle, theta. So let me write that. This is going to be equal to P cosine theta times displacement. And okay, how do I find FP? I don't know if FP is not given. What do I do?
I equal it to the mass of the ağırlığı of the back.
Yes. Gravitational force is equal to the FP, right? That's how he's lifting it. So maybe I can just write it like mg is equal to, supposing he's moving with constant velocity, cosine theta times d. And just to make things a little simpler, I can kind of see that. So this thing, cosine theta times d, this is d, this is theta. If you project this d to here, you also have properly define H. So I can actually write it like mgh. So, and if you put the numbers, H is equal to 10 meters, backpack is like 15 kilograms, and G is 9.8. I think I found something like 1470 joules, right? And so this was A. And B, we are supposed to calculate the work done by the gravity, right? The work done by gravity on the backpack. So it's exactly the same, but now, okay. Gravity is down, displacement is in this direction, and I need this angle. And if I project this angle to here, I see that gravity is in the opposite direction, right? So it's acting in the negative direction. So I need to put a minus sign, but it's in the opposite direction. Let's put that minus sign. So this is the mg, this is the cosine theta, and that's the same displacement d. Again, I'll use h for this. This is minus mgh, and this is going to be equal to minus 1400 around joules. And
I have
C,
a question, Hojam.
yes.
For part A and B,
Mhm.
do we only use the vertical displacement because it says that the motion has constant velocity?
Mhm.
So
Yes.
that means there is actually, okay, as it says, acceleration is 0, but that only applies to the horizontal displacement.
Yeah, I mean, like, I think acceleration is 0 in both horizontal and vertical, right? I think I assumed here there's no acceleration. So this hiker is moving with constant velocity along this direction. So that means like there's no acceleration in any direction.
Okay.
And you are absolutely right. If there was acceleration, things would be a little complicated, right? That's why I was able to take mg was equal to fp, because net force should be 0.
Yes.
Keep moving with constant velocity, exactly like you said.
All right, Hojam, thank you.
Thank you.
Hocam, I have a question.
Yes.
How did cosine theta times d became h?
Yeah, that's a little bit confusing, right? So here's the triangle I am looking at. So this is the triangle, and this is the theta, which was confusing because I actually used this theta to project f along this direction, and actually this same theta here, theta, to project mg to this direction. But when I saw cosine theta, okay, this is theta. When I saw cosine theta multiplied with d, I immediately said it must be equal to h because, okay, this distance, okay, maybe let me clean. So this distance times this angle is h, right? I can see this triangle. Is that clear?
Yes, better.
Yeah, thank you. So the net work done, let's calculate that. Net is equal to, okay, this is maybe the person's work. This is the work done by gravity. And the net work, I don't see any other work, so I need to just sum these two things. W of P plus W of G. And they are, okay, they're exactly the same thing with the minus sign. So the net work done must be equal to 0. Good.
Hocam, but our bike still has a potential energy.
So there is no potential energy, right? We didn't introduce that thing yet. So right now we identified forces. There's like gravitational force and the person's force. So of course we'll come to that. We'll talk about potential energy later in this course. But for the moment, Suppose we don't know anything about that. So right now I have only two forces, mg and p, and I calculated what I see here as a definition of the work. And I'm not saying anything about potential energy. I'm just saying the total work done on the object. And there are two works done, one done by the person, the other one done by the gravity. And if you sum these two things up, they are zero.
Okay hocam.
Mhm. I think this thing will be clearer later. I know you have habits of this, like when you see a height difference in potential energy, but I think it'll make sense just in a little bit. Maybe you have to be just a little bit patient. All right. Now let's introduce some machinery, because you can kind of see like there are like vectors. There's one kind of vector for the force, another kind of vector for displacement. And let's use how we calculate work, right? Definition of work like this is actually not pleasant. Every time you see a parallel, let's make it a little bit more systematic. So for this, I want to introduce so-called dot product. So let me just introduce it like this. Let's assume you have two vectors. And then I put an arrow and an object as we did so far. This means it's a vector. And I want to define this operation. Like here, you can see I put a dot here. So this dot is not the multiplication, as you know. This is like we call it scalar product. And let's say we are interested in scalar product of two vectors, A and B. I don't know A and B, but suppose they are given, okay? And I want to call this scalar, or maybe sometimes people call it dot product because it's a dot product. And of course, first thing I know is like I need to have a net result, which I get in the previous page, which was equal to force times displacement times the angle between these two things, cosine theta. Okay. If you like, you have some A and some, so let this be A, let this be B. These are vectors. And there's like some angle between them, theta. And the scalar product, I define it like this. And okay. Now let me introduce some vector components. Maybe a couple of things that we need to talk about. First of all, this thing, if you change the order, it doesn't change, right? A dot B is equal to B dot A. So that's a sensible mathematical operation. So we call it commutative. And it also has like this other nice property. So A dotted onto B plus C should be equal to A plus B dotted onto C. Okay. So when you have such properties, it's actually a nicer thing to work with, right? Because if you add B and C and make the dot product with A, this is exactly equal to adding A to B and taking the dot product with C. And this vector addition, you know very well how to do. Right? A vector added to another vector. So and now I want to introduce this, like, okay. Coordinates, let me call these, this is I, J, K, or if you like, this is X, Y, Z. And for A vector, I want to decompose it to its components. Let's call it AX times I hat plus AY times J hat plus AZ times K hat. And for B, I want to write exactly the same thing, BX, BY, BZ. This is I hat plus J hat plus K hat. Okay. And the nice thing about these like unit vectors, for example, if you take dot product of I with, I don't know, like say dot product of j, this is 0. And also dot product of I with k is 0. And dot product of j with k is also 0. Whereas dot product of I with itself, okay, this is dot product, this is 1. And so is dot product of j with itself. So is k with itself. Okay. So I can do this thing by one. I can take the dot product of this with this, this with this, and this with this. But I know dot product of this and this is going to be 0. So it is going to be term by term multiplication, which is very nice, right? I put 1 under the other one and I multiply it like this. So this thing, okay, let me write it, a dot b is going to be equal to ax bx plus ay by plus az bz. And as you can see, I also sum each product, right? I multiply ax with bx, ay with bvi, and az with bz, and I sum each of these separate products. And the result is scalar as it should be. Okay. Any questions about this? So this may look a little bit tedious, but actually you'll see it'll make a lot of things easier. All we need to remember is just this rule. If you see a vector, just decompose it and take products term by term. Okay, maybe I can.
You can ask something.
Yes.
How do we show the product vector? I mean, in general.
Like this?
Yes, and when we multiply to same direction.
So
and
you mean
what exactly do we get?
So if you multiply vector with, I didn't get the question. Can you say one more time?
I was trying to say, I mean, what is the final product looks like exactly?
Oh, I see. Like, I think it looks like a number, right? So you can take any vector you like in any direction, and the result is not a vector, it's just like a number. So you cannot draw it like this or like this. It is like a vector quantity, it's like scalar. What this means is you cannot draw it. It's just a number that you need to calculate. Okay? A scalar, by definition, doesn't have direction, right? No direction. And so we cannot draw and we cannot say how it looks. Does that make sense?
All right, thank you.
Mm-hmm.
I have a question, John.
Yes.
So I observed that the work done can be negative. What exactly does this mean? Because I know that work done is a scalar product and it doesn't have direction. So
yes.
How exactly does that work?
Yeah, good point. Thank you. So there's like a vector and like another vector, right? And so the definition is like this. It says, okay, just to remind you, if I put a vector, it is the vector itself. If I don't put a vector, I generally mean this is the magnitude of A, right? I mean, if you have a vector, you can put your ruler along it and then calculate its length, and that's the magnitude. And to make it brief, we generally show it with, rather than putting these like horizontal lines, I just put A without a vector. And similarly for B, this is also magnitude of B. So magnitude of A is always a positive constant. Magnitude of B is always a positive constant. And how come we have a negative, right? That's a good point. And we have a negative because of this cosine. So if this angle between these two vectors is less than pi over 2, we know cosine is positive, right? Then this result will be bigger than 0. So this is bigger than 0 if theta is between 0 and pi over 2. So if this angle is a little bit bigger than pi over 2, for example, let's draw it and see. Maybe pi is like, let this be perpendicular. If it is like this, now this is a long pi over 2, right? And I can immediately see this vector has a component which is opposite to the other vector. And cosine immediately takes care of that. The short answer is yes, it is negative because cosine is negative. And pictorially, it means one of the vectors has a component in the opposite direction of the other vector. Good?
All right, Hojam. So what exactly does that mean for us to have the work done be negative? Like, what does that imply?
That means you can either have like a positive work, which means you are putting in work, or you are taking work from the system, right? You can think of this way. If the work done is positive, of course, we will come to this in a little bit. We are going to define energy and work energy theorem. But if you do the work on something that's positive, but I think we know there is like an action reaction force, right? Things also do the work on other things, right?
See, so it actually depends on it depends on the object that we're taking into consideration.
It depends on the force and the displacement, right? And the object, of course, it depends on the object in a way. I mean, if the object moves in a certain way, that's how it defines the work. I think if you are feeling uneasy about this negative work, it's okay. I think you'll get used to that.
I understand better now, Hojam. Thank you.
Mm-hmm. So you don't need to worry about this sign. I think it doesn't need to be overemphasized. You will see, it can be positive and negative because it'll make sense when I introduce energy in a little bit. Okay, let's go through an example. So the force shown in figure 7 has a magnitude of Fb is equal to 20 Newton and makes an angle of 30 degrees to the ground. Calculate the work done by this force using equation 4 when the wagon is dragged 100 meters along the ground. I think I didn't copy the equation 4, but it is basically asking us to calculate work using the vectors. And for this, I want to decompose force into its components. Let me write this F vector done by P. It's going to have X and Y components. And this one is going to be, okay, let me call it Fp, magnitude of P times cosine theta times along I direction plus F of P times sine theta times J hat. We know how to decompose vectors very well now. And the displacement D is equal to, all right, let me call it like dx times I hat, displacement along x direction, plus dy times j hat, displacement along y direction. So now I know there is no displacement along y direction, so let me just put 0 here, because this thing is moving only along this direction. And from this, okay, just multiply term by term, work done is going to be equal to Fp times cosine theta times x, and this is going to be equal to 20 Newton times cosine theta, which is given to be 30 degrees, cosine 30 degrees, times dx, which is given to be 100 meters. And if you multiply these numbers, what did I find? Find something like 1,000 joules. Oh, yes, thank you. So this is 1,732 joules. Thank you, good job. That's why you should not trust these numbers I give you. You should fix it if I mess up. Thank you. Okay, so far I was using like constant force, and let's generalize this. Okay, let's generalize it to a force which is not necessarily constant. So now, okay, let's think of like a more generalized problem. Let's say our object moves in like some arbitrary path, like this blue line, and for the moment, let's suppose it's going in an XY plane. But it doesn't have to be. So why we took I dot j? Because of perpendicular, exactly, yes, because they are perpendicular to each other, so we take I dot j to be 0. So in the xy component, this object moves, and we assume the force is changing, it's not constant. So there's some force here, there's some other force here, another force here, and we would like to calculate the net work done by this changing force. So it's easy to do. What we think of is like we are thinking of dividing these little, like this whole path to little chunks, like this, for example. And we are assuming in this little path, the force is approximately constant. In the next path, there's another force, and we say the net force in this little chunk is approximately constant. Here, there's another force, which is approximately constant here, here, something like that. Here, it's something like that. Maybe here it changes direction, but it's constant. So what we do is we calculate these little works one by one. So I would write it something like this: work. Let me take work is equal to this first force and this delta L1. Actually, I don't want to write it like this every time, so maybe I can use this vector notation we introduced nicely. So I don't want to write these cosines, so this is F1 dot delta L1 plus F2 dot delta L2 plus F3 dot delta L3 plus dot all the way to the end. Let's call this Fn dot delta Ln. And I need to sum these things. So of course, the reasonable thing is to take these delta L's to go to 0. But when delta L goes to 0, this sum is going to be an integral. And the way we do this is like we say f, which depends on the path, dotted on the L. Okay, and we take it from A to B. Is that clear? So, okay, of course, what we learned is to decompose these forces, and I can decompose this integral too. So this means what this integral means is like, okay, from A to B, I have some F force, D Lx, right? Now there's no vector, plus from some A to B, Fy times D Ly, plus from A to B again, Fz DLz. I calculate, I had like one integral. Since they are vectors, I can calculate it in terms of 3 different integrals. And if you are scared of integrals, you shouldn't be, because the only integral we'll use is something like this. Maybe I can write it here. If you have an integral of, say, x to the n dx, integral is the opposite of derivative. And if you remember derivative, you already know integral. It is going to be equal to x n plus 1 divided by n plus 1. And if it's going from A to B, we just put the limits here, A to B, and that means this is B to the n plus 1 minus A to the n plus 1 divided by n plus 1. That's everything you need. Maybe I can make it blue so that you just look at this thing.
Hocam,
I'll
I didn't
continue.
understand. Sorry.
Uh-huh.
I didn't understand how can we take equal the work integral
So
where
this
from
one?
literal come. Yo, upper üstlük. The total works eşittir.
This
Equal to
one?
yes.
So I said, okay, let me calculate work done for each little piece. For example, the work done for this little piece is this one, because F is approximately constant for this little time. So that's why I have F1 times delta L1. For a little bit later time, I have another force here, which is F2. And there's a little bit of displacement, which is delta L2. And I take the dot product of these two. And a little bit later, I have like F3 and L3. I took the dot product of these. And so what I did is like I take this whole motion, like whole displacement, divided it in like infinitely many small displacements. And because this is infinitely small, F is constant in an infinitely small interval. That's why I wrote this like this. And at the end, I said, okay, I'm trying to find the network done from A to B. So then I need to sum all of these things. That's what I did. And as delta L goes to 0, this is the mathematical definition of integral. This actually should be from vector A to vector B, actually. Okay.
Okay, hocam. Thanks.
All right. Thank you. So here's the example. A person pulls on the spring in figure 10, stretching it 3.0 centimeters, which requires a maximum force of 75 Newton. How much work does the person do? Okay. This person is holding from here and stretching the spring, and we are trying to find how much work does the person do. So let me write W, the work, just to make sure it's the work done by person. Let me put P as an identifier is equal to, okay, this is equal to F. Okay, now I think we know this is going to be like a changing force, right? Because, you know, okay, maybe I can ask you, does anybody remember what the force on a spring was?
K times
Force on a
X.
spring? Yes. So, okay, force by the spring is minus kx. So spring always tries to pull you. Then if this force is in that direction, the force by the person should be in the opposite direction. So let me write it that way. That this is going to be equal to a person dot dx. So since spring is trying to pull this thing in that direction, the person should pull it in the other direction. So it's going to be plus kx. This is equal to, okay, kx. This is the force by the person times dx. And like say it's like from 0 to, I don't know, delta x, which is 3 centimeters. That's equal to, okay, I showed you how to take this integral. This is going to be 1/2 k x squared from 0 to delta x. And that's equal to 1/2 k delta x squared. And I can put parentheses here. Now my question to you, I don't know k. K is not given. How do I find k?
By dividing force with the length, I mean the stretch.
Exactly. Thank you. Exactly. So this is like this F max divided by delta x, which is maximum stretch. So this is going to be equal to 1/2 F max. Okay, the delta x is cancelled times delta x. Now I have everything. I know the maximum force 75 Newton and the maximum stretch 3.0 centimeters, and I know 1/2, so I can calculate this, and this is going to give me, right, what did I find? Okay, what I found is something like 1.1 joules, something like, maybe you can check that, 1.1 joules. If any corrections, let me know. And B, if instead the person compresses the spring rather than like stretching 3 centimeters, how much work does the person do? All right, here, okay, the force was in that direction and the displacement delta x was also in that direction. Now we are supposing the force is in that direction because the person is pushing it. You have to push the spring to compress. But now we see that the displacement here is also in that direction, right? So then I think we can say that, okay, this is A, this is B. So F and delta X, they are in the same direction, in the same direction. So the answer is exactly the same. WP is equal to 1.1 joule.
In the face-to-face exam, do we have to write the integral for A part because the lower limit of integral is 0? Do we have to write
So
integral,
in-
or just can we use the kx 1/2 kx square?
Yes, yes. I think you can. So you mean this part?
Yes.
So the lower limit of integral is 0 because it starts from x is equal to 0, right?
Yes.
Is that your question, or did I not get it?
Yes, that was my question.
Okay, good. Because the delta x, the spring is completely uncompressed or unstretched. So the spring is in equilibrium position, and there's no force on the spring. So the person should not be acting any force either because there's action reaction there. Good. Any other questions?
Hocam, I think the result should be 112.5 joules.
112.5 joules. Okay. I think 112.5 joules.
You know, it's calculated in if it's calculated in centimeters, we got that, but we should calculate in meters. Yours was
yes,
right,
yes,
actually.
yes.
Yours was right,
Good.
actually.
Okay, good.
Oh, okay.
Good. Yeah, that's a good point. That's also the lesson. Make sure you look at your units, okay? I always mess up with this thing. Okay. All right, now I want to introduce kinetic energy. Now we now know work, and let's just like increase the complexity just a little bit. And for that, I want to introduce the kinetic energy. And here is my setup. Suppose you have a car and it's going with some velocity, yes. And it's going with some velocity, V1, and there's some net force, F net. And there is some displacement, let's call this D, I don't know, maybe 100 meter, something like that. After that, I look at the car and I see that the car has like a new velocity, V2, and I want to study this problem, okay? And what do? I basically start with your favorite equation. Okay, what do I need to do? I am trying to find the work done on the car, and for that I will need the force on the car, but the force on the car is not given. And for that, I will use this equation everybody likes. Is V2 squared is equal to V1 squared plus 2 times A times delta X. We all like this equation, right? It's one of our favorites. And from here, I know A should be equal to V2 square minus V1 square divided by 2 times delta X. And now I know the force. Force is going to be equal to, of course, we are assuming constant force for the moment. I'll generalize it later. It is going to be equal to, F is equal to, of course, MA. So this is going to be M. Maybe I can write it a little bit nicely. This is 1/2. This is M, and A is equal to V2 squared minus V1 squared divided by delta X. And let me calculate work. Work is equal to F, okay, F net. This is F net dotted onto D, but they're in the same direction. So I can just write this is like F net times D, and this thing is going to be equal to, okay, I have F net, I have it there, 1/2 M V2 squared minus V1 squared divided by delta X is, let's put delta X is equal to D here, times D. So this is cancelled, and the result is 1/2. Let me write it separately, 1/2 M V2 squared minus 1/2 M V1 squared. So I see some structure here. So maybe I can define something new right now. Like I want to define this so-called translational kinetic energy. Kinetic means it's related to motion, and I want to call this thing K is equal to 1/2 M V squared. So if we have mass M and velocity V, kinetic energy is 1/2 mv squared. And okay, now I can kind of see this thing. This is equal to kinetic energy at the later time subtracted from the kinetic energy in the earlier time. And now I can define so-called work energy theorem. So this is work energy theorem, and it says the net work done on a system is equal to change in kinetic energy. That's called delta K, which means kinetic energy at final moment subtracted from kinetic energy in the initial moment. Okay, these two things are what we introduced. These are going to make our job a lot easier when we use them in problems. Now I want to generalize this thing for like, okay, now for changing force, let's write what we know. Force work is equal to F dot dl, right? Suppose everything is in the same direction to make things simple. And I know this is going to be equal to M times A, which is equal to dV dt times dl. And now I want to write it in a different form. I want to take M outside. I want to write this dV dt is equal to okay, I can use the chain rule. This is going to be dV dl times dl dt, right? So this is dV dl times, and what is dl dt? Does anybody know what dl dt is? This quantity?
Velocity.
Thank you. Yes, so this thing, maybe I can indicate. This thing is V, velocity. And now let's write everything together. So then this is going to be equal to V times dV dl times dl. Well, I can cancel these dl's, which amounts to changing the variable in the integral. So then, okay, this integral is m times v times dv from initial vi to final v final. But this is an elementary integral. You can just take by using what I showed you in the previous page, which is, okay, this is 1/2 v squared and the limits vi to v final, which will give you 1/2 m v final squared minus 1/2 m v initial squared. And this is exactly what we wrote here, the work energy theorem. So the work energy theorem is valid whether you have a constant force or changing force. All right, here's the example. A horizontal spring has a spring constant K is equal to 360 Newton per meter. And A, how much work is required to compress it from its uncompressed length, x is equal to 0, to x is equal to 11.0 centimeters. So maybe I can go ahead and start. I think we already studied spring and we know how it works. In the previous page, if you remember, the work done person was equal to 1/2, and we calculate F there, and it was like, I think, totally found something like that, right? K x squared. Let me just look and copy that. Right here. So the work done by this person was equal to this or this. Either was fine. So I'm going to use exactly that result. And this is equal to 1/2 K is 360 Newton per meter times x is equal to 11 centimeter, which is 0.11 meters squared. And if you multiply these numbers, what I find is 2.2 joules. And B, if a 1.85 kilogram block is placed against the spring and the spring is released, what will be the speed of the block when it separates from the spring at x is equal to 0? And we are supposed to ignore the friction. And B, any suggestions? How can I solve this one? So you compress, so initially you compress the spring, and now you place a block, and then you release. And when the block and the spring separate at x is equal to 0, we are trying to find the speed of the block. So how do I find the
Kinetic energy of the block and the work that friction
exactly?
make
Yes.
equal to
So,
the
yeah.
springs.
Let's use work energy theorem. So work energy theorem. It says work done on the block by the spring should be equal to change in kinetic energy. So the work done on the block by the spring is going to be, okay, this is a force of the spring and the displacement in the same direction. If I multiply these numbers, I'm going to find exactly the same thing I found here. So this thing, work done by the spring is, okay, this is 2.2 joules. And the change in kinetic energy, initially the block is at rest. So initial kinetic energy is 0, and final kinetic energy is 1/2 the final squared. Now I can solve, okay, I know the mass. This is like 1.85 kilogram. I can write this. This is 1.85 kilogram. I can solve this equation for VF. And what I found from here is, okay, this is going to be something like this. 2 times work done by spring on the block, okay, divided by mass. And if you do this calculation, I found 1.53 meter per second. So C, repeat part B, but assume that the block is moving on a table as in figure 18, and that some kind of constant drag force, Fd 7 Newton, is acting to slow it down, such as friction or parallel surface finger. So we are supposed to solve exactly the same problem, but now there's like a drag force. And for that, I need to calculate, okay, C. So work done on the block by the drag force should be calculated, which is what? I don't know, it says like, let's call it FD, but D, and I think the problem is making it easy for us by making it constant. But the key is drag force is always in the opposite direction, right? It's trying to slow it down, but the displacement is in this direction. But this whole thing is going to be negative because they are in the opposite directions. So let's remember that. So drag force is what? 7.0 Newton, 7.0 Newton times the displacement is again 11 centimeters, which is 0.11 meters. And I found from here, down block,
.77, but minus sign.
okay, minus 0.7 joules,
77.
right?
Yes.
Something like that. And now I need to use work energy theorem. Total work done by W net is equal to W by work done on the block by the spring plus work done on the block by drag force. And we already calculated the work done by spring. This is like 2.2 joules. And work done on the block by the drag force is like 0.7 joules. And this should be now equal to, by work energy theorem, 1/2 mv final squared, because initial kinetic energy is 0, and the final squared. And you can solve this for V final. But I found here, okay, maybe I can write it like this in the more general form. WP minus F drag times X divided by M. And if you multiply these numbers, you're going to find 1.23 meter per second. And we look at these two numbers. Okay, this is 1.23, this is 1.53. Okay, that makes sense. So we have smaller velocity due to friction as expected. All right, any questions? So the minus came from the following. So FT is acting in the opposite direction because it's trying to slow down. That's what the frictions do, right? Frictions are in the opposite direction to motion. But the motion is on this direction. And I said this should immediately be negative here. So push this a little bit. This is minus. Does that make sense?
Hocam,
The friction, yes.
it is actually comes from the formula, because in the formula there is a cosine theta. The
Yes,
cosine
yes.
theta is 180 degree. It is
Good.
-1.
Thank you. So this is like FD times cosine theta times D, but this is like 180 degrees. Thank you. And this is cosine theta of cosine of 180 degree is equal to -1. So this is going to be minus F drag times displacement. Thank you. It's also a good way to look at it. Any questions? Any objections? All right, let's do one final example and then you can go. Here's a problem. So there are two vectors, A and B, and we are supposed to calculate the angle between these two vectors. It's just an exercise with our dot product, newly learned dot product.
We have to multiply dot. We have to use dot product divided by its value product.
All right, let's
I
do
think.
the dot. Okay, good job. So let's do the dot. A dot B is by definition equal to magnitude of A times magnitude of B times cosine theta.
Yes,
And we'd like
exactly.
to find the angle, this angle. So for that, okay, we first need to multiply the vectors and find the left-hand side. And then we need to find the magnitude of A and the magnitude of B. Then we can solve this equation for theta. So let me first start with the dot product. Dot product is what? This is going to be this times this plus this times this plus this times this, right? Maybe I can write it. This is bx plus by by plus az bc. But this thing is equal to, okay, we can multiply these numbers. What did I find? Maybe I
91.4.
91.4.
Yes.
So this is the result. And now I need to calculate A. A, we know from Pythagorean theorem, is equal to, okay, x squared plus ay squared plus c squared. If you don't remember this, you can think of this to be like A dot A, like this is equivalent to A dot with itself and root. And if you do that, what did I find? Let me, I'll ask you to do it.
96.2.
96.2.
Yes.
Okay. And finally, I do the same thing for B, which is equal to, okay, B dot B. By the way, I think I strongly recommend you do these calculations because you know you have to do it in the exam. And if you never do it and try to do it in the exam, you know your fingers are not ready and it's likely that you'll have some trouble.
Hocam, I am sorry. It is not 96.2. It is 9.8. I couldn't.
90.8. Let me actually look at my answers.
No, 9.8.
9.8. Okay.
Yes. It is G value.
9.8. Good. So compare with what I found. So I found, yes, 9.8. B is equal to,
11.
I found 11.02, 11.0.
0.
Now, yeah, and now I can calculate cosine theta is equal to A dot B divided by A B, and this should be equal to 91.4 divided by 9.8 times 11.0, and from here you can calculate theta is equal to
32.
cosine minus 1 times this thing. Let me copy that, not try it again. And this is equal to 32 degrees. This is like a handy trick to find angles if you don't know them. Okay. Any questions? See, I have still more time, but maybe we can end it here and then continue tomorrow with, I think I have 2 more, maybe 3 more exercises. Because these are not difficult either. Right? Any questions, any comments?
Teacher, the sign of the AY multiplied by BY is negative, right?
Yes,
the-
yes, because yes, this one is minus, this one is plus, so this must be, the second one should be negative. Maybe I can, but I thought like this is negative, right? I thought it is embedded in the definition of AY. AY is minus 3.4.
No, and I know the definition is right. I just want to ask if.
Yes, yes, yes.
those are okay.
So this one is definitely negative. So this is, for example, this is negative times negative. This is going to be positive. Yeah, I think we should be careful with these signs because it's like a very common source of error in the final result.
Right, thank you.
Right, if no questions, I think I'm done for today. I'll see you guys tomorrow. Thanks for coming.